physical science. Today we're going to talk about gravity. So, the first thing we're going to do is review some of this force math that we have done in the past. So here it says, calculate the force necessary to accelerate at 1 meter per second squared a semi-truck with a mass of 5.56 tons. And it gives us the information that 1,000 kilograms equals 1 metric ton. So the first thing we need to do is convert our mass from tons to kilograms so that our math works out correctly. So we write down our given, 5.56 tons, converting from tons to kilograms. In 1 ton, there are 1,000 kilograms as per the given. So 5,560 kilograms. Now we can do step 1, write our equation. F equals ma. Both acceleration and force are vectors. Since we're solving force, we can just go ahead and substitute. Force equals 5,560 kilograms times 1.00 meter per second squared. The arithmetic is fairly simple. Our answer is 5,560 kilograms times meters per second squared gives us newtons. If you have questions about that, please leave them in the comments. We're going to move on to talk about gravity. Our objective today, as you can see, is describe the 4 fundamental forces of the universe and calculate gravity. So the first thing we need to do is talk about the 4 fundamental forces of the universe. So this little blackboard I have put up. There are 4 fundamental forces in the universe. We're going to list them in order from strongest to weakest. So the 4 fundamental forces of the universe. From strongest to weakest, once again, they are the strong nuclear force, which we'll talk about more in the future, but for now it's sufficient to say that this is the energy that holds, or the force that holds together the protons and neutrons in a nucleus of an atom. The second is the electromagnetic force. And you have some familiarity with this. This is the energy that, the force that holds magnets together, or even that repels magnets, as we'll talk about in a little while. And it's also the force that provides the power for my crappy YouTube videos. The third one is the weak nuclear force. And this one's a little bit spookier and harder to define, but basically the weak nuclear force is the force that can cause some subatomic particles to transmute to others, which is important in radioactive decay, but we'll get to that later in the year too. And the fourth, the weakest of the 4 fundamental forces is gravity. So once again, in order, these are strong on top, weakest on the bottom. However, even though gravity is the weakest, we can also sort them by range, and it's just reverse. So gravity is the longest range. It acts over the whole universe, as we'll get to in a second, to the strong nuclear force, which is the shortest range. The strong nuclear force, oftentimes for large atoms, doesn't even cover the span of one atom. It tapers off really quickly. It has a short range. Those are the 4 fundamental forces of the universe. You need to have these memorized in order from strongest to weakest. So, talking about gravity, we can say that gravity is a universal attractive force. Universal attractive force. So everything in the universe is attracted to everything else in the universe by gravity. That is, everything with mass in the universe is attracted to everything else with mass in the universe. It attracts all massive objects to one another. So this word massive, in our daily usage, massive means like great big. Like if I said I had a massive lunch, I probably didn't just have one potato chip. In physics, the word massive specifically means just with mass. So while in our normal usage we might say, wow, that's a massive truck, right? That's true in physics too, but even a small truck is massive in physics, right? Even a grain of sand is massive in physics, so it just means it has mass. So gravity tracks all massive objects, which is all objects with mass, to all other objects in the universe. It depends on, well, if it's attracting objects with mass, it depends on the object's masses. That's fairly simple. It also, since we talked about range earlier, it also depends on the distance between the objects. So as the mass of the objects we're considering increases, the strength of gravity between them increases. As the distance between them increases, the strength of gravity decreases. So mass and the force of gravity are directly proportional, and distance and the force of gravity are inversely proportional, but more specifically, they're proportional by the inverse square, which means as we get 2 units further away, the strength of gravity decreases by 4 units, as we'll see in our equation here. So here's the equation. F sub g, the force of gravity, or weight, they mean the same thing. F sub g equals capital G times m1 times m2 divided by d squared. We're going to write down what each of these variables means, and I want you to just measure it. So F sub g is weight, right? It stands for the force of gravity, but the force of gravity and weight are the same thing. Weight and mass are different. Mass is how much stuff there is in an object, right? Weight is how much the force of gravity affects an object. So they are related, right? On Earth's surface, if we're just thinking about Earth's surface, a more massive object also has more weight. In fact, for any location, a more massive object also has more weight. But weight has another variable involved, as we'll see in a second. So mass and weight are different, but the force of gravity and weight mean the same thing. Capital G is what we call the universal gravitational constant. Since it's a constant, we don't have to just write down the units, but we can also write down the exact value of this for our entire universe, right? The universal gravitational constant is true everywhere in our universe. It is 6.67 times 10 to the negative 11th meters squared newtons per kilogram squared. And that unit is almost meaningless, but it's that way so that the other units drop out, leaving us with newtons as our unit for weight. I'm going to move over here to talk about the other two quantities, or the other three quantities. So mass 1 and mass 2, these are both the masses of the objects. And they're measured in kilograms. And d is distance. Is distance. Measured in, you guessed it, meters. So let's do a math problem with those. So we'll say my teacup here has a mass of 1 kilogram. And we'll say my skull, my head, has a mass of 2 kilograms. We'll say they're 30 centimeters apart, right? So let's calculate the force of gravity between those two objects. So we write our equation first. F sub g equals capital G m1 m2 divided by d squared. Ignore that little mark there. I'll erase it. Maybe I'll erase it. Oh, that's not an eraser. Erase. Oh, okay, well that whole thing's gone now. Oh. Sorry. Okay, anyway, that's right. So now we're going to substitute in our numbers. So F sub g, which is what we're trying to calculate, the force of gravity between these two objects, equals 6.67 times 10 to the negative 11th kilograms squared newtons per meter squared, times 1 kilogram for the mass of my teacup, times 2 kilograms for the mass of my head, divided by 0.30 meters, this quantity squared. the 0.30 meters, that's 30 centimeters. I've just converted it to meters so that we can do the math and the units drop out. I'm going to use my TI Inspire CAS calculator, not a sponsor, to solve this problem. So I'm going to type into my calculator 6.67 times 10 to the negative 11th times, well, 1 times 2 is just 2, so I'm just going to type in 2, divided by the quantity 0.3 squared. The answer I come up with is F sub g equals 1.48 times 10 to the negative 9th. What's my unit? Well, kilograms drop out, meters drop out. We're left with, I'm sorry, this should have been meters squared per kilogram squared. Please forgive me. Anyway, they do drop out, leaving me with newtons. Is this a very large number or a very small number? Well, look, 10 to the negative 9th. That would be 0.80148, right? So it's an extremely small number. For reference, a newton is about the weight of a paperclip, something very small. So this is 8 orders of magnitude smaller than the weight of a paperclip, this force between these two objects. So that's why, even though technically these two objects exert a force on each other, we don't notice them moving because the force is so tiny. If you have any questions, please leave them in the comments. Have a great rest of your day.